On Monday afternoon, an asteroid with the dimensions of a large building will journey between Earth and the Moon, and its passage will go largely unnoticed. This, in itself, is not a cause for alarm. The object, named 2026 JH2, is projected to miss our planet entirely. The detail that should give us pause, however, is that its existence was completely unknown to us just a month ago. We only discovered it days before its close approach. And it is not the only object moving through our cosmic neighborhood this week. A subtle pattern is emerging in the data. Once you see this pattern, the word safe in every headline about this flyby begins to feel less reassuring, because its meaning in this context is not what you might assume. Stay with me, because we will explore the one thing that mainstream coverage seems reluctant to say aloud, a truth that has little to do with whether this particular rock hits us. If this story captures your curiosity, we invite you to follow our journey on calm space as we continue to explore these developments. We also love hearing where our viewers are watching from, so feel free to leave a comment. Now, let us begin. Part 1. The rock we almost didn't see. This Monday, an object estimated to be somewhere between 50 and 100 feet across will pass between our planet and the Moon. It will not be at the lunar distance, but significantly closer, traversing about a quarter of that span. And here is the fact that warrants a moment of reflection. This object was not on our charts a month ago, or even 2 weeks ago. Astronomers located it just days before its arrival. Not years, not months, but mere days. This raises a fundamental question about our awareness of the space around us. The asteroid is named 2026 JH2, and the story being told in the headlines is one of reassurance. A newly discovered asteroid, they say, will make a close but safe pass by Earth. In the strictest sense, this is accurate. Calculations of its trajectory confirm that this specific rock will not impact our planet. But this version of the story, with its calm surface, conceals the actual narrative. The true story is not about this individual asteroid at all. It is about the sobering reality that an object between 50 and 100 feet in size was able to approach so near to us. Our only knowledge of it is thanks to a fortunate observation, a faint smudge of moving light captured by a telescope just a few nights ago. Had that smudge been on a slightly different course, one that ended here instead of gliding past, we would have discovered it at the exact same time, leaving us with no opportunity to do anything at all. This is what this story is truly about. Not the asteroid, but the warning it represents, and whether the warnings we receive are worth anything at all. First, let us examine the hard numbers, because it is the numbers that make this event tangible. The asteroid, 2026 JH2, will reach its closest point to Earth on Monday, May 18th, at approximately 21:23 Universal Time. For the eastern United States, this is mid-afternoon. At that moment, it is expected to be around 56,700 miles from the center of our planet. While some orbital solutions place it a little farther, and others a little closer. That is the key figure to keep in mind. This precision allows us to visualize just how close this encounter will be. To truly understand whether 56,700 miles is close, we need something to compare it to. The most obvious point of reference is the Moon, which orbits Earth at an average distance of about 238,000 miles. This means the asteroid is passing at roughly 1/4 of the distance to the Moon, crossing deep inside its orbit. But there is another comparison, one that is rarely mentioned because it sounds like science fiction, though it is simple arithmetic. We have a ring of satellites in what is known as geostationary orbit, the communications and weather satellites that appear fixed over one spot on the planet. That ring is situated at an altitude of about 22,000 miles, while 2026 JH2 at 56,700 miles will pass outside this ring. it is still threading its way through our immediate celestial neighborhood, a region filled with the hardware humanity has launched into deep space over decades. It is not a distant speck, but a visitor crossing our yard. But how large is it? NASA's Jet Propulsion Laboratory estimates its diameter is somewhere between 50 and 100 feet. It is important to be honest about what this estimate truly is, because that honesty is vital for everything that follows. The 50 to 100 foot range is not a direct measurement. As of now, no radar beam has been focused on this object, and its heat signature has not been measured. The size estimate is derived from one thing only: how bright it appears in a telescope. You take that brightness, make an assumption about the reflectivity of its surface. A dark rock reflects less light, a lighter one reflects more, and then you work backward to calculate a size. This is the standard method for every newly discovered asteroid, and it always carries a wide margin for error until more precise data can be gathered. So when you hear 50 to 100 feet, what you are really hearing is a description of a faint, moving dot, and our best guess based on how dim it appears. The uncertainty is baked in. We are sizing an object we found 4 days ago based on a flicker of light. So, is an object 50 to 100 feet across dangerous? Here, we must resist two opposite and equally mistaken assumptions. The first mistake is to hear the word asteroid and immediately picture the fate of the dinosaurs. This is not that. An object of this size is not a planet killer or a civilization ender. It would not crack a continent. The second mistake, however, is the more common one. To hear 50 to 100 feet and think of it as basically nothing, just a harmless rock. That is also profoundly wrong. The truth, as is often the case, lies somewhere in between. To put this object into a reference class you will recognize, let us look back to February of 2013 over the Russian city of Chelyabinsk. An object came in that was roughly 60 feet across, placing it right in the middle of the size range we are discussing for Monday's asteroid. It did not even hit the ground. It exploded in the air, an event we call an airburst. That single airburst blew out windows across 6 cities and injured around 1,500 people. Almost every one of those injuries was from flying glass, from people who were standing at their windows looking up at the bright streak in the sky. When the shockwave arrived, it turned every pane in the city into shrapnel. All this from a rock the size of the one passing us on Monday, and it never even touched the surface. So no, 50 to 100 feet is not the end of the world, but it is not nothing. It is a city's worth of broken windows. It is a serious chunk of rock moving through near-Earth space at thousands of miles per hour. And if its trajectory had been different, Monday afternoon would have looked very different for somebody. There is one more piece of this object's basic profile, and it is the piece that connects to the larger pattern we are going to spend this time unpacking. 2026. JH2 has been classified as an Apollo-class near-Earth object. That may sound technical, so let me make it plain. This classification is not just a label. It is a key to unlocking the deeper story of where this object came from and why its path is so significant. To understand the significance of asteroids, we must first grasp their orbits. Among them, the Apollo class represents a special category of objects whose paths intersect with Earth's journey around the Sun. Imagine our planet's orbit as a fixed lane in space. While most asteroids remain far away in their own distinct region, the asteroid belt, an Apollo object, follows a different rule. Its long, elliptical orbit causes it to swing across our path, spending most of its time farther from the Sun than we are. But the inescapable geometry of its trajectory means it must periodically cross the very space our world travels through. This is what makes this particular class of asteroids so profoundly important. They are the most numerous of all orbit types that can intersect ours, and as a result, they account for the majority of close approaches and historical impacts on Earth. The asteroid known as 2026 JH2 is not some exotic visitor. It is a perfectly ordinary member of this single most consequential group of objects in our solar system. That word, ordinary, carries a quiet but immense weight. When we hear asteroid, our minds often conjure an image of something singular and rare, a dramatic, isolated event. But an Apollo-class object crossing Earth's orbital lane is not an event in this sense. It is a defining behavior of an entire population. There are a great many of them, and for them, crossing Earth's orbit is not an exception, but the very essence of what they are. Once this is understood, the way such a flyby is often reported can feel slightly misaligned. The story of 2026 JH2 is often framed as a unique discovery, a one-time curiosity. It is far more accurate, however, to see it as a single sample drawn from a vast and mostly unseen collection of similar objects. The only reason this specific member of the population became visible to us is that its moment of crossing our path happened to align with a telescope pointing in just the right direction at just the right time. Had our luck been different, but the rock itself unchanged, 2026 JH2 would have been just another uncounted object, passing silently in the dark, forever unnamed. This perspective, seeing it not as a discovery but as a sample, is the key to understanding the larger picture. It is also vital to be precise about an object's speed, as this factor helps determine the consequences of a potential arrival and reveals a pattern we will trace throughout this exploration. Relative to Earth, 2026 JH2 is traveling at approximately 9 kilometers per second. This is its closing speed with our planet, a figure that is difficult to intuitively grasp. To translate it into more familiar terms, 9 kilometers per second is in the range of 20,000 miles per hour. This is the incredible velocity at which this object and our world moved relative to one another as it threaded past us. By the standards of near-Earth objects, this is actually on the gentler side of the spectrum. These bodies can approach Earth at speeds ranging from just a few kilometers per second to as high as 30 or 40, and in the most extreme recorded instances, far faster. The kinetic energy an object carries increases with the square of that speed, meaning a faster rock of the same size will impact with exponentially greater force than a slower one. At around 9 kilometers per second, 2026 JH2 is therefore not the worst-case scenario. It is a moderately sized object, moving at a moderate closing speed, and yet it still warrants comparison to the Chelyabinsk event. This reference point is a sobering reminder that even the most unremarkable members of this cosmic population are far from harmless. So, how was this particular object found, and when? The discovery was the result of collaboration between astronomers at several facilities, two of which are worth mentioning for what they reveal about this process. One was the Farpoint Observatory in Waubonsee County, Kansas. The other was the Mount Lemmon Observatory, located high in the Santa Catalina Mountains north of Tucson, Arizona. It's important to note that these are not clandestine government installations. They are working observatories, integral parts of a global network of telescopes that patiently scan the sky every clear night. Their mission is to search for exactly these kinds of faint, moving points of light that were not there the previous night. They successfully detected 2026 JH2 and reported their findings. From there, the orbital mathematics were calculated, and the result was a confirmed close approach. What is most striking, however, is that the entire window from its first detection to its nearest point to Earth was measured not in months or years, but in days. To truly appreciate the situation, we must slow down and examine how such a detection actually occurs, as the mechanics of the process explain so much of what follows. An object like 2026 JH2 does not announce its presence. It isn't glowing or transmitting a signal. It is simply a dark piece of rock reflecting a tiny amount of sunlight across immense distances. From our vantage point on Earth, it appears as nothing more than an exceedingly faint dot, dimmer than the faintest stars most of us have ever seen, lost within a field of millions of other, similar dots. The method a survey telescope uses to find it is both simple and elegant. It captures repeated images of the same small patch of sky, just minutes apart, and then allows sophisticated software to compare them. In these short intervals, the distant stars and galaxies do not move, but an asteroid, being much closer and in motion relative to us, will have shifted its position from one frame to the next. It appears as a dot that walks. The software is programmed to flag these walking dots, after which an astronomer or an automated system confirms that the moving object is real and not a sensor glitch. Only then are its precise position measurements reported to the global clearinghouse that collects this data from around the world. Once a sufficient number of these position measurements have been gathered over a long enough period, the object's orbit can be calculated with confidence. And only then, after this entire chain of observation and analysis is complete, can we determine how close the object will come to Earth and when. The system is elegant, and it works, thanks to the real and careful science performed by the people who built and operate it. But one must notice the critical dependency at the very beginning of that chain. Everything that follows the orbital plot, the close approach prediction, the news headline, depends entirely on that faint dot being bright enough to be captured in one of those images in the first place. If the object is too dim, or if it is located in a part of the sky that is difficult to observe, the chain of discovery never even starts. In such a case, the object is not missed in the sense of being overlooked. It is missed because it was never detectable at all. The timing of when 2026 JH2 entered this chain of detection is the entire point. It was not identified a year ago, with its orbit slowly refined over months into a confident, long-range forecast. Instead, it entered the system just a few nights before its flyby. At the moment, it finally drew close enough and grew bright enough to become one of those walking dots. The span from first detection to its closest approach could be counted on one's fingers. This is not a criticism of the teams at Farpoint or Mount Lemmon. It is a fundamental reality of the search for near-Earth asteroids. The observatories that tracked asteroid 2026 JH2 performed their duties with precision and success. The object itself was simply not visible to our instruments until it was already in our immediate cosmic neighborhood. This single observation that it was undetectable until its final approach is perhaps the most critical takeaway from the entire event. It is a condition that is not unique to this particular asteroid, but rather the standard for an entire class of object. To truly grasp the implications, we must first understand why this is the case. The headline described it as newly discovered, a phrase whose full weight only lands when you appreciate what newly signifies in this context. It does not mean found last year and tracked since. It means identified just now, moments before its closest pass. It is essential to state clearly that this object poses no confirmed threat of impact. The current orbital projections show 2026 JH2 flying past our planet and continuing its journey back into the vastness of space. Monday's event is classified as a near miss, and in astronomical terms, such encounters are relatively common. However, the truly disquieting aspect of this event has little to do with whether this specific rock was on a collision course. The core issue is this: an asteroid between 50 and 100 feet in diameter was able to travel to within 1/4 of the Moon's distance from Earth, and our warning period was only a few days. Had its trajectory been aimed directly at our planet, that warning period would have been exactly the same. This raises the central question we must hold on to. If the system is working as designed, What happens when the next object of this size is not a near miss? When an unexpected event occurs, there is a natural tendency to assume that the system failed. Hearing that an asteroid came within a quarter of the lunar distance with only days of warning might lead one to believe that a mistake was made, a telescope was misaligned, or an agency was not paying attention. It is crucial to set this instinct aside, because the truth is more challenging. The system did not fail. The detection of 2026 JH2, just days before its closest approach, is, in fact, a demonstration of the system working exactly as it was intended. This is the normal, expected performance of our global asteroid detection network for an object of this size. No one made an error. This is simply what the apparatus is capable of. Once this reality is understood, the calm headlines about a routine flyby begin to feel far less reassuring. To understand why, we must first adjust our mental picture of how we track these celestial objects. A common perception exists of a comprehensive master list, a definitive catalogue containing every hazardous rock in our solar system, with its orbit precisely plotted and its arrival time calculated. In this imagined scenario, we are watching everything, and the list is essentially complete. This is not the situation we are in. What actually exists is a catalogue of near-Earth objects, painstakingly assembled over decades of observation. It contains tens of thousands of asteroids and represents a monumental scientific achievement. However, the completeness of this catalogue is not uniform across the board. Its coverage drops off dramatically as the objects in question become smaller. The reason for this disparity lies in simple physics. A larger asteroid, with its greater surface area, reflects more sunlight, making it brighter and therefore easier for our telescopes to detect from a great distance. Conversely, a smaller asteroid is fainter, dimmer, and significantly harder to spot against the black backdrop of space. Compounding this challenge is the fact that the population of smaller asteroids is exponentially larger than that of the big ones. This fundamental reality means our asteroid database is not one single unified catalogue. It is better understood as 3 separate inventories, sorted by size, each with a profoundly different level of completeness and trust. At the highest level are the largest objects, those measuring a kilometer across or more. These are the true civilization enders, asteroids with the potential not just to devastate a region but to alter the entire planet's climate, belonging to the same class as the one that led to the extinction of the dinosaurs. Here, there is genuinely good news. For this category of object, the catalogue is believed to be more than 90% complete. By our best estimates, we have found more than 9 out of every 10 of the asteroids large enough to cause a global catastrophe. We have mapped their orbits and can predict their movements far into the future. None of the known ones are on a collision course with Earth. This is a triumph of decades of patient survey work, a success that provides a crucial baseline of security. Moving down to the middle tier, however, the picture begins to change. This category includes objects around 140 meters and larger. While not planet killers, they fall into the regional devastation class. An impact from an object of this size could obliterate a city, generate a tsunami that erases a coastline, or flatten an area the size of a small country. Years ago, NASA was tasked with a goal to catalogue at least 2/3 of this population. That goal has not been met. The most recent estimates from the planetary defense community suggest that only about 40% of these 140-meter-plus objects have actually been found. This implies that for every 4 such city killers we have identified, another 6 remain undiscovered, their orbital paths completely unknown to us. The only way one of them enters our catalogue is if a survey telescope happens to catch its faint light as it passes by. Finally, we arrive at the bottom tier, the class to which 2026 JH2 belongs. These are objects in the tens of meters range, often referred to as the Chelyabinsk or Tunguska class, named after modern history's most significant impact events. For this size of object, the catalogue is not 90% complete, nor is it even 40% complete. It is almost entirely uncatalogued. We estimate that we have identified only a few percent, or possibly even less, of the total population of asteroids this size. The overwhelming majority of rocks in this range are simply unknown, their existence unrecorded until the moment they are close enough and bright enough to be detected by a survey telescope. That moment of detection, as we saw with 2026 JH2, typically occurs just days before their arrival. If the orbital geometry is favorable, we might get a few weeks' notice. And sometimes, in a possibility that is genuinely unsettling, the warning period is 0. Sometimes, the window of warning we receive is effectively 0. It is essential to understand that this gap in our defenses is not an arbitrary oversight. Instead, it is the direct and unavoidable result of two fundamental principles working in opposition to one another. The first of these principles is brightness. A larger celestial body will naturally reflect more sunlight, making it appear brighter in our telescopes. This allows us to spot it from a greater distance, which in turn means we can detect it sooner and track its trajectory for a longer period. Conversely, a smaller object reflects less light, appears dimmer, and can only be seen once it has already drawn uncomfortably close. The second principle is population. The smaller objects in our solar system do not just slightly outnumber the larger ones, they are overwhelmingly more numerous. There are relatively few large bodies, but an enormous population of smaller ones. This creates a deeply challenging paradox for astronomers. The very objects that are the most difficult to see are also, by a vast margin, the most plentiful. As a result, our catalogue of near-Earth objects is most complete precisely where there is the least to discover, and it is least complete where the population is densest. This is the fundamental reason why these gaps in our knowledge exist. This situation does not arise from a lack of effort or a decision to disregard smaller asteroids. The reality is that these small rocks are individually faint and collectively innumerable. Even with our most advanced survey telescopes, we can only ever register the ones that happen to wander close enough to Earth to cross our detection threshold for brightness. It's a crucial distinction to make. Our catalogue is not a comprehensive map of everything that is out there. Rather, it is a record of what has been bright enough for us to notice. It is worth stating that this is not for want of talent or dedication. The world's asteroid survey programs are operated by serious professionals who use truly impressive instrumentation. These are wide-field telescopes, built for the specific purpose of scanning immense portions of the sky each night and feeding that visual data into sophisticated detection software. Over the last 2 decades, these surveys have been responsible for a dramatic increase in the discovery rate of near-Earth objects. They are the reason our catalogue of large, potentially hazardous objects is as complete as it is a quiet but profound success story. However, these surveys are ground-based, and this comes with inherent limitations. There are a finite number of these facilities, and each can only observe the portion of the sky that is dark and above its local horizon. And all of them are contending with the fundamental problem of brightness and population that we've just explored. They have been given a monumental task, equipped with a powerful, but ultimately limited set of tools. The resulting catalogue, with its excellent coverage at the top for large objects and its nearly empty state at the bottom for small ones, is the honest reflection of that reality. This is what performing this job to the best of our current ability looks like. This leads us to the most unsettling part of the picture. Our system has a blind spot. This is not a metaphor for a small gap in our knowledge. It is a literal, physical blind spot in the sky. Our survey telescopes are located on the ground. They operate at night, looking outward into the darkness, away from the Sunday. This is simply how telescopes must work. You cannot spot a faint asteroid against the brilliance of the daytime sky any more than you can see faint stars. The overwhelming glare of our own star drowns out everything else. This means there is an entire region of space, the area between Earth and the Sun, that is effectively invisible to our ground-based surveys. An asteroid approaching us from that sunward direction, emerging from the Sun's glare, is something our network of telescopes on the ground simply cannot see. It remains hidden until it has already flown past us into the night side of the planet, or, in the worst-case scenario, until it is already entering our atmosphere. This is not a hypothetical scenario. It is precisely what occurred over the city of Chelyabinsk. In a previous discussion, I mentioned the Chelyabinsk event, a 60-foot rock that injured 1,500 people and shattered windows across 6 cities. But here is the detail I held back until now. That object was not detected by anyone. Not a single telescope, not one survey, and not one astronomer saw it before it streaked into the atmosphere over Russia. The warning time for Chelyabinsk was 0. The reason for this complete failure of detection was the blind spot. It arrived from the direction of the sun, hidden in the light of the daytime sky. The very first instruments to register its existence were the thousands of dashboard and security cameras that captured its fiery descent. This is not a story from some distant, technologically primitive past. This happened in 2013, well into the era of our modern sophisticated survey programs. An object with the power to cause widespread damage entered the atmosphere above a populated city, and our entire global detection system was unaware. It was unaware because the rock approached from the one direction we are unable to look. It is important to truly feel the shape of this problem, as it reframes the entire context of asteroid flybys. We have a survey network that diligently watches the night sky. It is effective, and it is the sole reason we even know about an object like 2026 JH2. But this network, by its very nature, is only observing half of a sphere, the half that looks outward into deep space, away from the Sunday. The other half, the hemisphere that contains the direct line between Earth and the Sun, remains largely unmonitored from the ground. An object on an orbit that brings it toward us from that sunward angle is approaching through a corridor that our telescopes cannot observe without being blinded by the sun's light. So, when we speak of our catalogue being nearly empty for smaller objects, there is a second, critical layer to this problem. It is not just that small objects are inherently faint. It is that even a small object that would otherwise be bright enough to detect becomes completely invisible to us if its path happens to bring it from the sunward side. This blind spot is not some minor gap at the edge of our coverage. It is an entire approach corridor that remains unwatched. The unsettling truth of the Chelyabinsk event is that it is not a freak occurrence we tell to dramatize a remote possibility. It is the recent, documented, and real example of an object using that exact corridor to arrive undetected. It did not slip through a small crack in our defenses. It traveled down the one major celestial highway that we have no cameras pointed at. It must be said plainly that nothing in the laws of orbital mechanics suggests that this sunward corridor is a rare path for an asteroid to take. Objects likely approach from the direction of the sun all the time. The issue is that those are the very ones we do not get to count because we are unable to see them. This means our very perception of how often this happens is itself shaped by the blind spot. In a very real sense, we are attempting to estimate the frequency of an event using an instrument that is incapable of detecting that event. How can we fully grasp a risk that our tools are designed to miss? So, when I say that the system is working as designed, this is what I mean. The design itself has a known, structural, and physical limitation. We can only ever hope to catch the objects that are bright enough, positioned far enough from the sun's glare and well placed enough to appear in a night sky telescope. The asteroid 2026, JH2, met all of those conditions, just barely, and just in time for us to get a few days' notice. A great many objects of a similar size do not meet those conditions at all. And our catalogue is a direct reflection of this reality. It is excellent at the top, for the large and easy-to-spot objects. It is shaky in the middle, and it is nearly empty at the bottom, where 2026 JH2 resides. The few days of warning we received for its approach is not a fluke, nor is it a failure of the system. For an object of this size and faintness, that is the number. That is what success looks like right now. The calm headlines we sometimes see, announcing that a newly discovered asteroid will safely pass Earth, can mask a far less comforting reality. When translated honestly, such a statement reveals that our detection systems have managed to spot one of the smaller objects just in time to watch it go by. This isn't a failure. It represents the system working at its peak, constrained by the laws of physics. The true problem, the one that is never part of the headline, is what happens times after times the warning is issued. The detection side is doing what it can, but if finding the object is only the first step, it forces us to confront the much harder question, now what? To understand the gravity of that question, imagine the warning is real. This is not a drill, not a near miss, but the genuine article. On some ordinary night, a survey telescope detects a faint point of light moving where none was before. Over the next few observations, its orbit is calculated, and the answer that comes back is not a relief. The object is not going to miss. It is on a collision course. The warning time you have is precisely what these objects give you. For a body in the tens of meters class, it might be only days. For a city-destroying object, the warning could be longer, but only if we are lucky enough to have spotted it on a previous pass. The detection system has performed its job flawlessly. The alert goes out. And in that moment, only one question matters. The very question this entire exploration has been leading to. What can we actually do? The honest answer, the one that never makes it into those reassuring news reports, is almost nothing. As of today, in the real world, there is no operational system capable of taking an asteroid warning and translating it into a successful deflection. There is no fleet of interceptors waiting on launch pads, no established protocol with a button to press. Nowhere on Earth does a standing capability exist to convert a detection into a physical action on a timeline of weeks or even months. What we possess is the result of a single, successful science experiment. The gap between that one test and a functional planetary defense system is enormous, and contemplating that gap reveals a truly terrifying implication about our current vulnerability. This is not to say, however, that we have done nothing. It is crucial to acknowledge what has been achieved, for it is genuinely impressive. In 2021, NASA launched a mission called DART, an acronym for the Double Asteroid Redirection Test. The mission's purpose was as straightforward and audacious as its name implies: to intentionally fly a spacecraft directly into an asteroid. The goal of this deliberate, high-speed collision was to see if the impact could measurably change the asteroid's path through space. The target for this groundbreaking test was chosen with meticulous care. It was a near-Earth asteroid named Didymos, which has a small moonlet, Dimorphos, in orbit around it. This smaller companion, roughly the size of a stadium, was the ultimate destination for the DART probe. In September of 2022, traveling at thousands of miles per hour, the spacecraft slammed directly into Dimorphos, and it worked. The mission was a spectacular success. The impact measurably altered Dimorphos's orbit around its parent asteroid, shortening the time it took to complete one revolution. This was not a trivial, barely detectable change. It was clear, significant, and observable from Earth. DART proved, for the first time, what had only ever been theory, that a kinetic impactor, a sophisticated way of saying crashing one thing into another, can indeed alter an asteroid's orbit. This is a monumental achievement. It represents a turning point for our species. For the first time in the 4.5 billion year history of this planet being struck by rocks from space, humanity reached out and intentionally altered the path of a celestial body. It was a profound demonstration of our technological potential. But to truly understand our current state of readiness, we must also look at everything the DART mission was not. It is here that our sense of comfort begins to run out. DART was a single test, conducted against one specific, carefully selected, and conveniently located object. The target was chosen precisely because its unique binary setup made the results of the impact easy to measure. The mission itself was planned over many years, years of design, years of construction, years of flight time. It was a demonstration performed under ideal, pre-arranged conditions, with all the time needed to ensure success. This is the equivalent of proving in a controlled laboratory experiment that water can put out a fire. While that is a true and vital principle to establish, it is not the same as having a fire department. It is not the same as having trucks, hoses, trained crews, and a system that guarantees a response within minutes. DART proved the principle, but nothing has yet been built upon it. There is no fire department for asteroids, only a single, brilliant demonstration that the physics works, leaving a void where an operational capability should be. The specific reason the target was chosen tells us so much about how far we are from true readiness. Dimorphos, the moonlit DART struck, was not picked because it was a threat. It was picked because it was a perfect tool for measurement. Its clean, regular orbit around Didymos acts like the steady hand of a clock. By nudging the moonlet, scientists could simply watch that clock to see if its timing sped up or slowed down. The entire experiment was designed to produce a readable result, which was the right call for a science test. A real threat, however, would not come pre-packaged for easy analysis. It would likely be a single object on a collision course with Earth, with no convenient orbiting partner to serve as a clock. The question would no longer be, can we measure a change? It would be, can we produce a large enough change, aimed with enough precision and with enough lead time to turn a certain hit into a definite miss? DART did not answer that question. It answered a narrower, friendlier one, and it answered it well. But that was only a first step, and a first step with no second is not a capability. It is a proof of concept, sitting on a shelf. There is also a quieter problem buried within this challenge, and it is the problem of variety. Asteroids are not all the same kind of object. They are incredibly diverse. Some are solid, monolithic bodies of rock. Others are more like loosely bound piles of rubble, little more than gravel held together by their own faint gravity. Some are dense and rich in metal, while others are porous and fragile. This incredible variation introduces a profound complication, raising the question of how a single deflection method could possibly be effective against such a wide array of potential threats. How an object reacts when struck, whether the force transfers efficiently into a new trajectory or simply gets absorbed in a cloud of ejected material, is deeply dependent on its composition. The DART mission successfully impacted a single object of a specific type. While this provided invaluable real-world data, it left a crucial question unanswered. How would other kinds of asteroids behave? A truly effective planetary defense system must be prepared for any type of threat that appears, not just the one we've managed to test. This reveals that the proof offered by DART, while significant, represents just one data point in a vast and largely uncharted territory of possibilities. It's a reminder that the journey from this initial demonstration to a fully operational defense is not a small step, but a vast chasm yet to be crossed. The challenge isn't merely one of engineering and construction. It is rooted in the fundamental physics of deflecting a celestial body. The physics of diverting an asteroid's path is an unforgiving science. There is no way to simply stop an object of this mass, nor can it be vaporized into a harmless cloud. Attempting to do so would only transform a single, predictable threat into 1,000 smaller ones, all following the same deadly trajectory. The only viable strategy, the one demonstrated by DART, is to alter its velocity by an incredibly small margin, a gentle nudge. The true power of this nudge is unlocked by the patient force of time. By adjusting the asteroid's speed by a mere fraction, that minuscule difference is allowed to accumulate with each successive orbit around the Sunday. Over years, a change that began as a hair's breadth deviation grows and compounds, eventually becoming the critical margin between a direct impact with Earth and a safe passage. The nudge itself is subtle. The true instrument of change is time. This entire deflection strategy, however elegant, is completely reliant on having an abundance of time. Now, consider this requirement against the reality of our current detection capabilities. For objects tens of meters in size, our warning time can be as short as a few days. The kinetic impactor method, the one approach we have successfully tested, demands years of advance notice to be effective, allowing its small push to compound into a significant course correction. Yet, the warning systems we have for these small to medium-sized bodies often provide alerts measured in days or months. This reveals a fundamental and dangerous disconnect at the heart of planetary defense. The only proven tool in our arsenal requires a long runway, but the alarms we receive often signal an imminent approach. The method and the warning are profoundly out of sync. At this point, a natural question arises. If we lack the time to nudge an asteroid, why not simply destroy it with overwhelming force? The intuition is powerful, but the reality is that destruction is often the worst possible course of action. It's crucial to understand why this seemingly simple solution is so perilous. When you shatter a single incoming object that is on a collision course, you haven't eliminated the danger, you have multiplied it. What you are left with is a swarm of fragments, and the center of mass of that swarm continues, on average, along the very same impact trajectory. The act of breaking something apart does not alter the ultimate destination of its pieces. Instead of a single impact that could potentially be modeled and its effects predicted, you now face a barrage of smaller impacts scattered across a much wider region. Depending on the timing and geometry, a contained, localized event could be transformed into a devastating regional shotgun blast. To be clear, there are very specific, narrow scenarios where fracturing the object might be the least terrible option. This is generally when the warning time is so short that no gentle method could possibly succeed, and the object is small enough that breaking it into pieces genuinely mitigates the total harm. But these are extreme edge cases. The mainstream, well-considered approaches to planetary defense all operate on a different principle. Methods like the kinetic impactor, or the more gradual gravity tractor, where a spacecraft flies alongside an asteroid, using its own minuscule gravity to tow it onto a new path over a long period, are all designed to gently alter the object's course, while it is still a great distance from Earth. Their common, non-negotiable requirement is time. There is simply no tool in the established planetary defense framework that is effective with only a short warning. The entire field is predicated on the assumption of having years of lead time, an assumption that our current capabilities cannot always guarantee. The problem, then, is not a single vulnerability, but two distinct gaps that dangerously amplify one another. First, there is a detection gap. Our catalogue of smaller objects is far from complete, and the corridor of space, sunward of Earth, remains a blind spot, meaning we often get very short notice. Second, there is a response gap. Our only proven deflection method requires a long warning period, and no operational system has been built to deploy even that. The truly perilous aspect is how these two deficiencies interlock. If our detection systems were robust enough to find every potential threat years in advance, the response gap would be less critical. We would have the time to improvise a solution. Conversely, if we had a rapid and powerful response system that could act on weeks of notice, the detection gap would be more manageable, as short warnings would still be sufficient. We currently have neither. We are left with short warnings and a tool that requires a long lead time, and the entire existential risk resides in the space between them. This void between our awareness and our capability has an unspoken name, a scenario all too easy to imagine. We found it, and there was nothing we could do. Let us set aside dramatic fiction and consider the realistic projection, which is somehow more unsettling in its plausibility. If a city-threatening asteroid were discovered tomorrow, with only a few weeks or months of warning, the world's reaction would not be a swift, decisive launch. It would be a frantic scramble. It would involve the planet's space agencies attempting to improvise a mission from the ground up, designing, building, and launching a deflection mission against an unforgiving clock. They would have no pre-built hardware, no rehearsed procedures, and no tested plan for this exact object. All the while, the fundamental physics of deflection, which rewards patience and foresight, would work against them, becoming less forgiving with each passing day. It is conceivable that something could be assembled. Human ingenuity can be extraordinary when facing unthinkable consequences. But to be merely possible is not the same as being prepared. When we confront the question of our readiness for an asteroid threat, the honest answer is that we are not prepared. This is the deeper implication of an event like the flyby of 2026 JH2. The object itself will not harm anyone, but the calm and reassuring story we tell about these close, safe passes deliberately leaves a piece out. That missing piece is the admission that our safety was a matter of luck, not capability. The asteroid's trajectory missed us. We did not steer it away, nor could we have. Should the next object's path prove to be a direct one, the few days of warning we would likely receive would be time to watch, not time to act. We have proven we can nudge a distant, predictable rock, but we have not constructed anything that could deflect an imminent threat discovered at the last minute. This is the gap in our defenses. The remainder of our journey is about why that gap is not a simple oversight, why it will not fix itself, and why the sky this week is filled with more than just one passing stone. The story of 2026 JH2 deepens considerably when we learn that it is not arriving alone. Its passage is part of a larger phenomenon that transforms a single flyby into an event you need to understand. What is happening this week is not about one rock, it is about a wave. During the same period that 2026 JH2 makes its approach, the public asteroid tracking lists, tables assembled from JPL's data and republished by monitoring sites, have lit up with an unusual crowd. This week, it is not one object passing inside the moon's orbit, but closer to 8 of them. To grasp the meaning of that number, it needs a baseline. A single asteroid passing within the Earth-Moon distance is common, occurring many times each year, and is not, by itself, news. What is far less common, and genuinely on the high end of what seasoned observers see, is a cluster of 8 such flybys in a single week. This has been flagged by independent trackers who follow these lists as a regular practice. One commentator who monitors this data noted that he first took notice when 3 asteroids were projected to pass inside the lunar distance across just 4 days, a fact he considered remarkable on its own. Then, within roughly a week, the total count of objects passing closer than the moon had climbed to around 8. He described it as one of the densest weeks of sub-lunar flybys he had seen in all his time watching. This is not an attempt to dramatize a normal week. The week itself is unusual, and the people who watch these tables for a living are saying so. So, what is in this wave? The objects are all small near-Earth asteroids, from the same general population as 2026 JH2. They even carry similar designations, a series of 2026 J names, because they were mostly discovered recently in this same observing season. There is 2026 JK2, an object roughly 80 feet, or 26 meters, across, making its closest approach on May 15th at about 1.24 lunar distances. It is also moving fast, at around 20.5 kilometers per second relative to Earth. Following it is a string of others, with designations like JM2, JU1, JX1, JF2, JD1, JV1, and JT. The majority of these will pass within or just beyond 1 lunar distance across the span of May 14th through the 20th. And then there is 2026 JH2 itself, our Monday object, positioned right at the close end of that entire group, making one of the nearest passes of the entire wave. We should pause on those designations for a moment, because the J series of names is quietly telling you something. The provisional naming system works like this. The year comes first, and then a pair of letters encodes when in that year the object was found. That cluster of J letters means all of these objects were discovered in the same recent stretch of time. They were not sitting in a catalogue for years, tracked and understood. They were found, essentially, right now, in the final run-up to their own flybys, just as 2026 JH2 was. The wave is not 8 objects we had been following. It is 8 objects we discovered on their way in. Each one is a small version of the same story, found late, because late discovery is what our current system produces. This is not just a cluster of flybys. It is a cluster of short-notice discoveries, a demonstration of the detection gap happening 8 times in a row, in real time. It is also worth being clear-eyed about the sizes of the objects in this wave, because a couple of them are not trivial. At around 26 meters, 2026 JK2 is comparable in scale to the Chelyabinsk object, and its high speed means it carries proportionally more energy. 2026 JH2 itself, at 50 to 100 feet, is in the same conversation. These are not boulders, nor are they the pebble-sized debris that burns up harmlessly as shooting stars. Several of the objects in this week's wave are large enough that, on a different trajectory, they would represent a serious event for anyone underneath. It is vital to state that none of them is on that trajectory. This needs to be repeated, because it is true and it matters. None of these 8 is going to hit us, but their sizes are a reminder that this wave is not a cute astronomical footnote. It is 8 objects, several of them genuinely consequential in size, that we did not know about until they were nearly here, all passing through our neighborhood in a single week. The harmlessness of this particular event is a fact about these particular trajectories. It is not a fact about the system that found them. Now, this is where the story gets genuinely interesting, and where a picture begins to form. There is a public tool, the NASA Orbit Visualizer, that allows you to take any of these objects and plot its entire orbit around the Sun. When you take the 8 objects from this week's wave and plot all their orbits together on the same diagram, something immediately jumps out. At the far points of their orbits, away from us, the paths look nothing alike. They have different shapes. Some are stretched into long ellipses, while others are rounder. They have different sizes, and, therefore, different orbital periods, as the time it takes each one to circle the Sun is unique. Finally, they are all tilted at different angles to the flat plane in which the planets mostly travel. This incredible diversity raises a compelling question. How did a group of objects with such different origins and journeys all manage to arrive at the same small patch of space at the exact same time? Out in the vastness of the solar system, 8 objects are traveling along what appear to be 8 entirely separate paths. By any standard astronomical measure, they are unrelated. Yet, as their orbits are traced inward toward the Sun, a strange pattern emerges. They all converge. Their trajectories draw together, crowding into a remarkably tight zone of space, a region that happens to coincide precisely with Earth's own orbital path. What is most striking is that these 8 orbits, so different from one another in deep space, all bend toward this same narrow corridor where our planet resides. And the convergence is not just spatial, it is also temporal. Several of these objects pass through this zone within a day or two of each other, arriving in loosely associated pairs. They move like a cluster of cars passing through the same intersection, rather than being spread out evenly over time. There is one more subtle pattern woven into this data, a detail that will prove critical later. The objects that pass closest to Earth also tend to have the lowest relative velocities. They are moving more slowly with respect to us. In contrast, those that pass at a greater distance, like the fast-moving 2026 JK2 with its high orbital inclination, are the faster, more steeply tilted travelers. The closest ones are the slow ones. This is a vital clue, pointing towards something far larger than the events of a single week. Let's make sure that clue is perfectly clear, as it forms the very foundation of what follows. Imagine 2 different objects approaching the same crowded region of space near Earth. The first is moving quickly relative to our planet, its orbit sharply angled, cutting across the flat plane of the solar system. The second object is moving slowly, its path lying nearly parallel to Earth's own orbit. Which of these 2 is more likely to make a truly close approach? The answer lies in their dynamics. The fast, steeply tilted object simply slices through our region of space and is gone in an instant. But the slow object, traveling on a similar plane, lingers in our cosmic neighborhood, moving almost alongside us. It is this slower companion that has the opportunity to drift in for a much closer encounter. When we examine this week's wave of asteroids, this is precisely the sorting effect we observe. The nearest passes, including 2026 JH2, are the slower objects with flatter orbits. The more distant passes are reserved for the faster bodies with more inclined trajectories. This is not a random distribution. The fact that slow and flat orbits result in closer approaches, while fast and tilted ones stay farther away, is the visible signature of a real physical process at work. This pattern, this sorting mechanism, is not just a curiosity, it is a fingerprint. In the next part, I will show you that this process has a name, and it is the very same force that was instrumental in building the planet beneath your feet. This wave of asteroids is more than just 8 rocks. It is 8 rocks arranged in a pattern that tells a profound story. However, I must be careful here, and I want to be transparent about a serious objection to this interpretation. The most honest version of this story must include this counter-argument, and I will not hide it. The objection is this. Of course, these orbits all converge near Earth. We are only aware of these objects' existence because they came near Earth in the first place. We detected them precisely because their journey brought them through our neighborhood, where they became bright enough and close enough for our telescopes to spot. So, is the convergence of their orbits on our location truly meaningful? Or is it merely an obvious consequence of our method of discovery? This is a powerful and valid objection. If you only pay attention to the cars that drive past your own house, you should not be astonished to find that all the cars you have ever noticed have, in fact, driven past your house. This is the strongest counterargument to the idea that this wave of asteroids holds any deeper significance, and I want you to keep it in mind. We will confront it directly and fairly when we explore alternative explanations. For now, the short version of the rebuttal, which I will expand upon later, is that this objection is both partly correct and partly incomplete. It is a real factor, but it does not explain everything. Specifically, it fails to account for why this particular week is so unusually crowded with objects. But let's set that objection aside for a moment. Whether this wave is a genuine concentration of objects or partly an artifact of how we observe the sky, it accomplishes one thing that is not in dispute. It takes the abstract problem of asteroid detection and makes it terrifyingly concrete. When you strip everything else away, what is this wave, really? It is 8 rocks that we were able to see. These are the objects that happened to be bright enough, positioned correctly, and far enough from the sun's blinding glare to appear in our telescopes this week. This wave represents the visible portion of a much larger reality. And every single point we have made about the catalogue being nearly empty for objects of this size, everything we have discussed about the sunward blind spot, and everything we know about events like Chelyabinsk arriving with zero warning, all of that remains true, operating silently beneath this visible wave. The 8 asteroids we are tracking are not the only 8 that exist. They are simply the 8 that were catchable this week. If 8 catchable objects came through in a single week, then the honest question we must ask is not about the danger posed by these specific 8, none of which will hit us. The honest question, the one that connects this event back to the core of our investigation, is this. If this is the visible portion, what is the size of the portion we cannot see? And what would a few days of warning truly be worth against an object emerging from that invisible half? The wave does not change the answer to that question. It simply makes it impossible to continue treating the question as if it were merely an abstract exercise. Part 5. How the solar system builds things. I want to guide you away from the fear for a few moments, because there is something genuinely beautiful buried within this story. Understanding it will fundamentally change how you perceive that convergence we just discussed. The 8 orbits bending in toward Earth's path are not just a coincidence to be nervous about. They are a small, living, present-day example of one of the most profound processes in the entire solar system, the same process that assembled the world you are standing on. Once you see this, the wave stops looking like an omen and starts looking like a window into creation. So, let me pose the question that planetary scientists have been wrestling with for a very long time. How did the planets form in the first place? You begin with a young star, surrounded by a vast, thin, spread-out cloud of gas and dust. And somehow, over immense spans of time, that diffuse smear of material consolidates into 8 distinct planets, each one a compact sphere orbiting in a neat, orderly, flat plane. How does this happen? The intuitive answer, the one most of us recall from school, is gravity. Gravity pulled everything together. And while gravity is undeniably a crucial part of the story, it is not the whole story. Gravity is real, and gravity matters, but the full explanation is far more intricate. When we attempt to model the formation of a solar system from a diffuse cloud of gas collapsing under its own weight, we quickly encounter significant problems. Gravity, after all, is by a vast margin the weakest of the fundamental forces. It is not at all obvious that a thin, spread-out cloud would possess enough self-attraction to pull itself down into solid planets. Moreover, a pure gravitational collapse struggles to explain the other orderly patterns we see. The regular spacing of the planets, their differing densities, and how the entire system settled into a flat, organized disk rather than a chaotic swarm. This simple story has long been known to have holes. An alternative, older concept associated with the Swedish physicist Hannes Alfvén and his work on plasma cosmology and accretion theory proposes a different mechanism. This idea may be the key to explaining the convergence we see today. This alternative model explores what happens when a vast population of small bodies, countless particles, grains, pebbles, and rocks all inhabit the same region of space, each following its own orbit around a central mass. These objects do not remain in their pristine orbits undisturbed forever. Instead, they constantly interact with one another. The key to this model lies not in a single grand collapse, but in the countless, subtle interactions between these individual components. Sometimes, these interactions are direct collisions, where two bodies physically meet. Other times, it is merely a gravitational nudge as they pass near each other. There is a common assumption about what happens when objects meet in space, that they bounce elastically, like billiard balls, and perhaps shatter into fragments. While such events do happen, they are not the most significant outcome over long periods. The more consequential type of interaction, over vast timescales, is the inelastic one, the kind that does not result in a clean bounce, but instead bleeds energy out of the system. It is this subtle loss of energy that holds the secret to the system's evolution. Every time one of these inelastic, energy-losing interactions occurs, it has a tendency to make the orbits of the involved objects more similar to each other. This happens in three specific ways. First, the orbits become more circular and less stretched out, meaning their eccentricity decreases. Second, the orbits flatten and settle toward a common plane, reducing their inclination. And third, the objects begin moving more slowly with respect to one another as their relative velocities drop. Through this statistical process, a kind of cosmic herdsmanship, a population that began as a chaotic swarm is gradually guided toward orbits that are rounder, flatter, and gentler relative to their neighbors. Now, let us hold that result up against a recent astronomical observation. In a recent wave of objects passing through our system, those that came closest to Earth were the slow, flat ones, while those that remained farther away were the fast, steeply tilted ones. This is precisely what the herding process would lead us to expect. It predicts that objects which have undergone more of these inelastic interactions will be the ones with lower eccentricity, lower inclination, and lower relative velocity. In other words, rounder, flatter, and slower. The alignment between theory and observation here is striking. These are precisely the properties that allow an object to ease in close to Earth rather than punching through the system at a sharp, disruptive angle. So the sorting you see in the wave slow and flat ends up near, fast and tilted stays far is not a coincidence or mere noise. It is what you would expect to see if the objects are at different stages of this exact convergence process. The ones that came closest are, in a sense, further along on their journey. More of their chaotic, energetic orbital motion has been ground down toward the gentle, flat, slow state that the process inevitably drives everything toward. The wave is not just 8 rocks near Earth. It is 8 rocks caught at visibly different points along the same road, and that road leads toward convergence. The pattern is a fingerprint of the process itself, showing its hand. It is worth pausing to consider why these energy-losing, inelastic interactions are the ones that dominate in the long run, especially since the billiard ball intuition is so stubborn. When two small bodies in space encounter each other, the meeting is almost never a clean, elastic bounce. Real rocks are not perfectly rigid spheres. They crush slightly, they grind, they may shed material, they radiate away a little heat. Every one of these is a channel for energy to leave the encounter. And critically, the energy that gets lost is the energy of relative motion, the very energy that was keeping the two objects on different paths. Once that energy is lost, the two paths begin to drift toward each other. On any single encounter, the effect is tiny, almost nothing. But the solar system does not run on single encounters. It runs on enormous numbers of encounters over enormous spans of time. And a tiny effect, when applied a near infinite number of times, is not a tiny effect anymore. It is a current, it is a direction. And the direction always points the same way, toward less relative energy, toward convergence. This is what gives the process a direction at all. Fragmentation, the shattering of objects, does happen, and it scatters things and adds relative energy. But it is the equivalent of swimming against the current. The convergence is the current itself. Once a group of objects is moving slowly relative to each other, sharing nearly the same circular orbit in nearly the same plane, something can finally happen that could not happen before. They can come together and stick instead of shattering. Gentle accretion becomes possible. When things moving slowly touch, they do not blow each other apart, they merge. This crucial step is what finally allows for growth. And now, a clear route to building planets emerges. Infalling material, like gas and dust, becomes ionized and is shaped by the system's rotation and magnetic fields, condensing first into grains. These grains accumulate into pebbles, pebbles into meteoroid-sized chunks, and those into asteroids. Through this very same process of convergence and gentling, asteroids are drawn together into larger bodies called planetesimals. In the denser streams of material, these planetesimals can grow rapidly, sweeping up everything in their lane and becoming planets. The whole hierarchy, from dust to worlds, is driven by this engine, the slow, statistical herding of orbits towards sameness, followed by gentle merger. But is this elegant picture merely a compelling story, or is it supported by tangible proof? It has evidence, and the best piece of it is sitting in our own solar system, in the asteroid belt. There is a popular image of the asteroid belt as the wreckage of a planet that exploded, but the truth may be far more interesting. A world that once circled the sun between Mars and Jupiter, only to be violently shattered, leaving behind a trail of cosmic debris. It is a powerful and dramatic image, but it is also one that is almost certainly incorrect. The reasons why this narrative fails tell us something profound about our solar system. For starters, if you were to gather every single object in the asteroid belt and combine them, their total mass would only equal about 1% of the Earth's. This is not the remnant of a full-fledged planet. It is barely the leftover material from a small moon. The numbers simply do not support the idea of a lost world. Furthermore, the distribution of this material presents another problem for the exploded planet theory. When scientists measure the density of matter across the belt's orbital zone, it is roughly an order of magnitude lower than that of its neighbors, the inner planets and Jupiter. A planet's cataclysmic end would not produce a signature so vastly different from the regions around it. To account for the missing mass, one would have to imagine it being flung entirely out of the solar system, an act that would require a staggering amount of energy to overcome the deep gravitational well of the Sunday. The accretion model, however, fits the available data perfectly. The asteroid belt does not look like the aftermath of an explosion. It looks like a process of planetary formation that began, but was ultimately halted. It appears to be a place where the slow dance of gathering and merging started, but never reached its conclusion. The most likely reason for this interruption is the immense gravity of nearby Jupiter, which constantly stirred the region. This gravitational influence kept the relative velocities of the fledgling objects too high, and their orbits too unstable for them to gently combine. The fingerprint of this stalled accretion is written clearly in the belt's structure. The dwarf planet Ceres, a single object, contains approximately 1/3 of the entire belt's mass. If you include the next 3 largest bodies, you have accounted for the vast majority of all the mass in the region. The countless thousands of smaller asteroids are merely the remaining fragments. This is not the signature of an explosion, which would scatter mass more evenly. Instead, it is the clear signature of a few winners' bodies that progressed far enough in the process of convergence to begin sweeping up their neighbors, growing at the expense of all others before the entire process was frozen in time. Ceres offers us a glimpse of what a planet looks like when its formation is interrupted midway. The composition of the asteroids themselves provides its own powerful argument against the exploded planet hypothesis. The belt is not composed of one uniform type of material, as the fragments of a single shattered world would be. Instead, it contains a rich variety of compositions, from rocky and metal-rich bodies to dark, carbonaceous objects. There is even good reason to believe it harbors celestial travelers' bodies that were nudged inward from the cold, outer solar system, and perhaps even the occasional visitor captured from interstellar space. A shattered planet would be relatively homogeneous, all pieces of a single whole. The belt, by contrast, is a diverse collection, a mixture of objects with different origins and histories that happen to occupy the same region of space. This is precisely what an accretion zone looks like, a place where material from many sources is slowly being gathered and sorted, not a place where one object came apart. Everywhere one looks in the belt, the evidence points toward the same conclusion. This is not a wreck, but a construction site where work was indefinitely paused. This same logic can be seen operating in regions far beyond the belt, out past the orbit of Neptune. In the frigid outer reaches of the solar system lies another vast population of icy bodies, dwarf planets, comets, and innumerable smaller objects. That region, too, resembles a place where accretion proceeded partway and then slowed, where a few larger bodies managed to gather some material, but the process never culminated in the formation of full-sized planets. Seen through this lens, the solar system is not a finished, static creation with a few leftover crumbs. It is a dynamic process, caught at a particular moment in time. The inner solar system largely completed its accretion long ago, with the material in those orbital lanes coalescing into the planets we know today. The asteroid belt and the outer regions are the zones where this process stalled, allowing us to see the intermediate stages, the triumphant few that grew largest, and the vast, ungathered remainder, all frozen in place like a film, paused partway through. The near-Earth asteroids, the population to which 2026 JH2 belongs, are objects that have been knocked out of these stalled regions. They are now sent on wandering orbits that cross our own pieces of unfinished work, drifting through a lane where the work did finish, the lane that became our planet Earth. This brings the story back to the present, to the asteroid 2026 JH2 and the recent wave of flybys. That cluster of near-Earth objects, with their orbits bending to converge on Earth's path, is a small, observable example of these very same dynamics at play today. It is crucial to be clear. This does not mean these objects are about to merge and form a new world. The point is quite the opposite, and it is both more reassuring and more sobering. The convergence of orbits near a massive body is not strange, nor is it an omen that something is wrong. It is simply how our solar system has always operated, at every scale, from dust grains to planets. Earth sits in its orbital lane, and its gravity, like that of any massive body, naturally focuses and shepherds the population of smaller objects that pass nearby. Over immense timescales, the orbits of these objects statistically tend toward convergence. We know precisely what the long-term outcome of this orbital convergence is, because we are standing on it. The outcome is accretion. The outcome is impacts. For its entire 4-5 billion year existence, Earth has been accreting this material. The craters that scar its surface are the visible record of this process, while the far greater number of craters erased by erosion, oceans, and the slow churn of plate tectonics form the invisible record. This is the profound implication, stated plainly. The recent wave of flybys, it has been running for eons, and Earth is still right in the middle of it. The rocks continue to converge, because convergence is the fundamental rule, not the exception. In this entire cosmic equation, the only variable that human beings have any influence over is whether we can see the next one coming, and whether we can do anything about it when we do. The solar system's part in this story is already written. Our own is yet to be determined. For billions of years, the cosmos has operated on its own schedule, and it will continue to do so for billions more. Our role, our brief window of observation and action, is the only variable we can influence. Yet, as we have established, our ability to see is limited, and our capacity to act is often an illusion. The cosmic accretion of matter never ceases. The only real question is whether we are prepared when it is our turn to face it. To truly grasp the stakes, we must move beyond abstract discussions of orbital mechanics and lunar distances. Before exploring what we cannot yet do, it is essential to ground ourselves in what these objects are capable of when they arrive. Let us consider two real-world events, two celestial bodies that did not miss, and allow them to set the scale for our understanding. The first is a name you may already recognize, Chelyabinsk. In February of 2013, an object, approximately 60 feet in diameter, entered the atmosphere over Russia's southern Ural region. This asteroid was squarely within the size range of the one discussed in our previous segment. It never struck the ground. Instead, it detonated in an airburst at high altitude, releasing an explosive force estimated at 400 to 500 kilotons, an energy output many times greater than the bomb that fell on Hiroshima. The resulting shockwave radiated outward, shattering windows across 6 different cities and injuring roughly 1,500 people. The mechanism of these injuries holds a vital lesson. No one was harmed by the rock itself. The injuries were caused by glass, from people who witnessed a streak of light momentarily brighter than the sun. They did the most natural thing imaginable. They went to the window to look. Minutes later, when the shockwave arrived, it transformed those panes of glass into a spray of flying shards. This was the result of a 60-foot object on the lower end of the scale we are considering, and it arrived with zero warning, emerging from the sunward blind spot where it was invisible to our telescopes. Our second event is older and far larger. In June of 1908, in a remote part of Siberia, the Tunguska event unfolded. The object responsible was larger than the one at Chelyabinsk, estimated to be somewhere between 160 and 200 feet across, though perhaps not as much larger as is commonly believed. It too exploded in the air rather than forming a crater, but the energy of the Tunguska airburst was orders of magnitude greater, estimated in the range of several megatons, possibly exceeding 10 megatons. This blast flattened an estimated 830 square miles of forest, knocking down trees like matchsticks, with all of them pointing away from the epicenter. This area of devastation is larger than many major cities and their entire metropolitan regions. The only reason the Tunguska event is remembered as a scientific curiosity instead of one of the worst disasters in recorded history is its location. It happened over a nearly uninhabited expanse of Siberian wilderness. Had that same object detonated over a populated city, our conversation today would be profoundly different. Tunguska represents the upper limit of what these smaller bodies can achieve, even without being large enough to be classified as a regional devastation threat. It is simply what a couple hundred feet of rock can do. There is a crucial lesson embedded in both of these events that is easy to overlook. Neither the Chelyabinsk nor the Tunguska object actually cratered the Earth's surface. Both unleashed their destructive energy as an airburst. Many people hear this and feel a sense of relief, as if an airburst is a gentler alternative to a direct impact. It is not. The airburst is the very mechanism of the damage. When an object of this size enters the atmosphere at incredible speed, the air in front of it cannot move out of the way quickly enough. It compresses violently, and the object effectively detonates from the immense stress and heat. This process converts its forward motion into a sudden, enormous release of energy high above the ground. That energy then propagates downward and outward as a powerful shockwave and a pulse of intense heat. The broken glass across 6 Russian cities was the product of Chelyabinsk's shockwave. The 830 square miles of flattened forest was the signature of Tunguska's. An object does not need to touch the ground to inflict catastrophic damage upon it. It only needs to arrive. So, when you hear in the future that a near-Earth object would probably result in an airburst rather than an impact, do not file this information under good news. It should be filed under, this is the form the damage will take. And then, remember that the object passing by on Monday is in the same size class as the one that exploded over Chelyabinsk. Remember too that the city-killer asteroids, of which we have only catalogued about 40%, are well above the scale of the Tunguska event. With this context, we must ask ourselves how comfortable the phrase "probably an airburst" really makes us feel. Hiding within both of these stories is a geographic accident, a factor we have been relying on, whether we choose to admit it or not. The Chelyabinsk event occurred over a city and injured 1,500 people, but the outcome could have been far worse. The object entered at a shallow angle, which spread its energy out rather than concentrating it on a single point. Tunguska, a multi-megaton blast that leveled an area the size of a metropolis, had a death toll of virtually zero, purely because of where it happened to land. In both cases, the factor that determined whether we speak of a tragedy or a footnote was not our detection systems, nor our response capabilities, because we had neither at the ready. It was luck. It was geography. It was a matter of where, on a mostly empty planet, the rock happened to fall. This uncomfortable reality underpins the reassuring statistics we often hear. When people say that impacts of a certain magnitude only occur every few decades or every few centuries, that framing quietly assumes our luck will hold. It presumes that the next one will also land harmlessly in an ocean, a desert, or a remote forest. Because most of our planet's surface is unpopulated, this assumption has, for the most part, proven true. But planning around the hope that our luck continues is not a plan. It is simply the absence of one, dressed up in the comforting language of frequency and probability. So this is the scale of the threat. An object like 2026, JH2, measuring between 50 and 100 feet, exists on a spectrum between a routine occurrence and the power of Chelyabinsk. The 140 meter class of city killers, of which we have found only about 40%, represents a danger well beyond that of Tunguska. These are not abstractions. They are shattered windows and flattened forests, and if they arrive in the wrong place, they are much, much worse. It is vital to hold this scale in mind because it is the very thing that gives the next subject its weight. And that subject is the stories we tell ourselves, the narratives people create, to make all of this feel more manageable, or perhaps more meaningful, than it truly is. For whenever a story like this one circulates a near miss, a close flyby, a new warning, it never travels alone. An occurrence like this travels with a set of alternative interpretations, and it is worth exploring them honestly. Some contain a genuine insight, while others, even if they miss the mark, deserve a clear and respectful answer rather than simple dismissal. Here on Calm Space, we do not promote these ideas as fact, but we also do not pretend the impulse behind them is foolish, because it is usually quite the opposite. It is the impulse of pattern recognition, one of the most powerful tools the human mind possesses. It just needs to be guided by discipline. The first alternative framing is the most compelling, so much so that it is less a conspiracy and more of a scientific objection. As promised earlier when we discussed the wave of asteroids, this point deserves to be addressed fairly. The objection posits that this wave is merely a product of observer bias. We have only identified these 8 objects, the argument goes, because their paths brought them near our planet. Therefore, the convergence of their orbits on Earth is not a profound discovery, but a tautology, a statement that is true by its very definition. It is a feature built into the fact that proximity to Earth was the prerequisite for their detection in the first place. It is essential to state clearly that this objection is partially correct. Anyone who claims otherwise is not being entirely forthright. The phenomenon of observational selection bias absolutely inflates the apparent convergence of these orbits. If the only celestial rocks you are able to see are the ones that fly close to you, then it stands to reason that every rock you have documented does, in fact, fly close to you. This effect is real, and its influence must be carefully subtracted before we can draw any grand conclusions. But this is also where the objection begins to fall short of a complete explanation. Once we account for this selection effect, the entire phenomenon does not simply disappear. For one thing, bias alone does not explain the timing density of the encounters. Why should this specific week be so much more crowded with flybys than a typical week? Observational bias is a relatively constant factor from one week to the next, and should not produce such a sudden and pronounced cluster. Furthermore, there is well-established mainstream physics describing how small bodies genuinely group together in ways that are not illusory. These are the very dynamics we have explored, from the gravitational focusing of Earth and other planets to orbital resonances and slow, large-scale clustering. These are real forces at play in the solar system. So, the most honest and complete answer is this. The convergence we observe is a genuine phenomenon. It is partly an artifact of our methods of observation, and it is partly a true window into the real dynamics of the cosmos. The crucial work of teasing apart how much is artifact and how much is reality is not a settled matter. It is an active and fascinating question at the forefront of research. This nuanced position is ultimately more interesting than either the breathless, uncritical version or the cynical, dismissive one. The second interpretation is far broader in scope, and you will often see it surface during weeks like this one. It is the idea that the asteroid wave is intrinsically connected to everything else happening to our planet right now. This view suggests that the incoming rocks, a stream of solar wind from a hole in the sun's corona, an impending geomagnetic storm, the current alignment of Mercury with the Sun and Earth, and a recent string of volcanic and seismic activity are all facets of a single, unified event. One great convergence of energies, a meaningful cosmic pattern. The appeal of this narrative is undeniable. The human mind instinctively resists coincidence. When several significant events happen at once, our intuition screams that they must be connected by a common cause. This is precisely the moment, however, when discipline must temper instinct. The honest answer is that these are almost certainly independent systems that just happen to be active at the same time. The asteroid flybys are governed by the elegant laws of orbital mechanics, gravity, and momentum, which were understood centuries ago. Those laws have nothing to say about solar wind. The coming geomagnetic storm is driven by charged particles flowing from the sun, and the behavior of those particles is entirely unrelated to the location of a rocky body in its orbit. The planetary alignment is a real geometric event. The planets do indeed form a line in space, but the gravitational and tidal influence of a small, distant world like Mercury on either the Earth or a near-Earth asteroid is many orders of magnitude too weak to organize asteroid flybys or trigger earthquakes. The numbers are not just different, they exist in separate universes of scale. On the specific question of whether solar activity can trigger earthquakes, a recurring theme in this framing the peer-reviewed scientific literature has found, at most, weak statistical correlations, never a deterministic trigger. The energy budget argument truly settles the matter. The elastic strain energy released in a major earthquake is immense, dwarfing by a vast margin any plausible amount of energy that space weather could conceivably couple into the planet's crust. The simultaneity of these events is real. Several things are genuinely happening at once, but it is a critical error to mistake simultaneous for connected. Independent systems constantly overlap in time. That is simply what it looks like to live on a dynamic planet where a great deal is always going on. The pattern recognition instinct fires, as it should, but the job of discipline is to then ask if a plausible physical mechanism exists. In this case, it does not. Let us put a number on the tidal force, because concrete figures are often the only thing that can quiet such an emotionally resonant idea. The strength of a tidal pull, the stretching influence one body exerts on another, falls off with extraordinary speed. Its effect decreases with the cube of the distance. If you double the distance to an object, its tidal effect on you is not halved. It becomes 1/8 of what it was. The moon raises powerful tides on Earth because it is so very close. The sun raises a smaller, but still significant tide, because its enormous mass compensates for its great distance. But a small planet like Mercury, tens of millions of miles away, even at its closest, exerts a tidal influence on Earth that is so vanishingly small it is lost in the noise. It is far, far weaker than the moon's pull, and even weaker than the everyday variations in the moon's own pull as it moves through its orbit. It simply cannot be the lever that organizes anything on our world. The same logic applies in reverse to its influence on a passing asteroid. When an alignment occurs, the geometry is real. The planets are, from our perspective, in a line. But a line is just a line. It is a visual arrangement, a trick of perspective, not a physical conduit of force. The forces involved do not spike just because the dots on a cosmic map have been neatly arranged for our viewing pleasure. The arrangement is something we notice. It is not something the asteroids feel. This distinction between what our minds perceive and what the objects themselves physically experience is the entire key to navigating this framing with both honesty and respect. The instinct to see the alignment as meaningful comes from the same place as good science, the powerful, essential instinct to look for structure in the universe. A third, more unsettling interpretation suggests that the late discovery of 2026 JH2 points to something sinister, the idea that a genuinely dangerous object is being deliberately concealed. This narrative frames the asteroid's late detection not as a failure of our systems, but as suspicious evidence of a cover-up. The answer to this, however, is found within the very structure of how we watch the skies, and it is a structure that is ultimately reassuring. The detection of 2026 JH2 was not the work of a single, secret entity, but came from independent observatories in different states. These observations were then published into a public data system, accessible to anyone. The tables charting close approaches are open for all to see, republished by numerous outlets. Around the world, amateur and professional astronomers across many nations and even rival institutions track these objects independently and relentlessly. The structure of the scientific community itself provides the most compelling counter-argument. A genuine concealment of a real threat would demand an almost impossible level of coordination among all these competing, independent and international groups. It would require every single one to agree to silence in a field where professional reward is built on being the first to identify something important. The late discovery, therefore, is not evidence of a conspiracy. It is evidence of the very capability gap this entire subject explores. The simple explanation that our survey system for smaller objects is incomplete and that we found it late because that is what the system currently yields is not only true, but far more useful. It points to a problem we can actually fix, whereas a cover-up theory offers nothing but a sense of unease. The real story encourages us to ask for better telescopes. A fourth perspective centers on the idea of planetary defense, but it splits into two distinct narratives. The first is a cynical view, which argues that since we can do nothing about an impact, public awareness is pointless and ignorance is bliss. The second is a conspiratorial version, suggesting that the technology to deflect these objects already exists in secret and is being withheld from the public. Let us examine both of these ideas. Regarding secret technology, there is simply no evidence of a hidden deflection capability. The DART mission represents the true public state-of-the-art, and what it demonstrated was a single successful test with no operational system yet built from its findings. The actual situation, a proven concept but no deployed system, is concerning enough without inventing a hidden one. As for the cynical notion that awareness is pointless, this perspective overlooks a crucial reality. Awareness is the very opposite of pointless. It is the engine of progress. Detection is the one component of planetary defense that is genuinely effective and consistently improving. The reason to pay attention to a flyby on a Monday afternoon is that public attention is what ultimately funds the surveys, and the surveys are the part of the system that is succeeding. Far from being bliss, ignorance is what allows budgets to stagnate and progress to halt. The case for seeing with greater clarity and for finally building the tools to act is made precisely by events like this one. That case can only be made if people are paying attention. The cynical framing, therefore, doesn't just surrender to the problem. It surrenders the one tool that is actively working to solve it. When we examine these different narratives, a common thread emerges. The most truthful account of 2026 JH2 is also the least dramatic, and yet it remains the most deeply unsettling. There is no hidden hand, no mysterious convergence of energies, and no cover-up. There is only a real rock, found late because our current system is designed in a way that makes late discoveries inevitable. It passed us safely this time, but the scale of what these objects can do, from the broken glass of Chelyabinsk to the flattened forests of Tunguska, is a stark and undeniable reality. This is why the simple truth offers no real comfort. The boring truth is that we are watching the sky with an instrument that has a known blind spot, and we are standing behind it with no fire department on call. This is not a conspiracy that can be exposed and fixed by its revelation. It is a structural problem that can only be fixed by building something new, a task we have not yet begun. Let us now assemble these pieces into a complete, realistic scenario. Here, we can see the entire picture, not as a disaster movie, but as a sober assessment of our current state. This is not a story of countdown clocks and square-jawed heroes, but the version that logically follows from everything we have explored. Its power lies in the fact that nothing in it is exaggerated. On some ordinary night, perhaps this year or the next, a survey telescope quietly scanning the darkness will detect a faint, moving point of light. It was not there the night before. Over the next few observations, enough data will be gathered to calculate its orbit. When the answer comes back, it will not be a near miss. The answer will be an intersection. An object of a significant size is on a path that will occupy the same point in space as Earth at the same time. The system has worked exactly as intended, which is precisely what makes the outcome so chilling. The telescope spotted the object, and the mathematics confirmed its trajectory. We now find ourselves standing in the exact situation this entire exploration has been leading toward. The warning time we have is the typical warning time these objects provide. For an object in the tens of meters class, that might only be days. For something larger, in the city killer class, it might be longer if we were fortunate enough to have spotted it on a previous pass years ago. It could be months, or it could also be alarmingly short. The alert goes out, and we are left with the one question that matters above all others. What can we actually do? The answer, based on our current capabilities, is a sobering one. We have one proven tool in our arsenal, the kinetic impactor, often called the nudge. The DART mission demonstrated its effectiveness, but it is a tool with a specific and non-negotiable requirement: time. The way the nudge works is by being applied very early, allowing a tiny change in the object's velocity to compound, orbit after orbit, into a large change in its final position. This is what creates the difference between a direct hit and a safe miss. The nudge itself is small. Time is the great multiplier that makes it effective. If you take away that time, the nudge remains just a nudge, insufficient to move the rock far enough. The one tool we have proven works needs years of runway to be reliable, a resource that a late discovery simply cannot provide. For the very objects most likely to catch us by surprise, the warning we receive may only be days or months. This creates a fundamental paradox at the heart of planetary defense. The warning time we get and the response time we need are profoundly mismatched. In a realistic scenario, there would be no orderly launch of a pre-built interceptor from a waiting launch pad. No rehearsed procedure for this specific asteroid on its unique trajectory would exist. Instead, what would unfold is a desperate scramble. The world's space agencies, not known for rapid coordination even under ideal circumstances, would be forced to improvise a deflection mission from scratch. They would face the monumental task of designing, building, and launching hardware that doesn't yet exist, all for a crisis that was never anticipated. With each passing week, the physics of deflection would become more demanding, as the precious time needed for a small nudge to alter an asteroid's course slips away. While humanity can achieve incredible things, when faced with an unthinkable alternative, relying on maybe is not a strategy. The difference between what is possible and what we are prepared for is vast. And when asked if we are truly ready today, the honest answer is no. To understand why this scramble is so much more difficult than one might imagine, we must look past the sense of urgency and consider the unchangeable realities of time. Certain processes simply cannot be accelerated, no matter how motivated the global effort. Constructing a spacecraft, even a relatively simple one, is not something that can be accomplished in a few weeks. The process involves a long sequence of design, component sourcing, careful assembly, and rigorous testing. This final step is critical because a mission that fails en route to its target is far worse than no mission at all. It represents a squandered launch and, most importantly, irretrievable time. Beyond the spacecraft itself, there is the launch, which must be scheduled around other missions and must wait for a viable launch window. This is the specific period when the geometric alignment between our planet and the target allows for an achievable trajectory. Even after a successful launch, the journey itself is long. Spacecraft do not travel instantly. They require months, or sometimes longer, to traverse the vast distances of interplanetary space. So, even in the most optimistic scenario, you are contending with an additive timeline. Design time, plus build time, plus testing, plus the wait for a launch window, plus the long travel time. All of this must be subtracted from a warning period that was measured in days to months to begin with. The arithmetic often fails to balance. It's not that such a mission would fail for lack of trying. It would fail because the clock ran out before the race could even begin. This sobering reality forms the entire basis for a proactive approach to planetary defense. The argument is simple. Any work that cannot be compressed during a crisis must be completed beforehand. Having hardware already designed, tested, and understood is essential. Having rehearsed procedures and pre-planned mission profiles is not a luxury, but a necessity. These preparatory stages represent the parts of the timeline that are incompressible. If this work is done in advance, then when a genuine warning arrives, the scramble is no longer about inventing a response from scratch. Instead, it is focused only on the launch and the flight. This is the crucial distinction between having a fire department and merely possessing a detailed theory of combustion. A fire department's value is not in its unique knowledge, but in its readiness. The trucks are already built, the crews are already trained, and the response can be measured in minutes. At present, our planetary defense strategy has the theory, but it does not yet have the department. The scramble scenario is simply a detailed portrait of what it means to confront a fire armed only with a theory. To illustrate this difference, it helps to consider a contrasting case: the near-Earth asteroid known as Apophis, This object is in an entirely different category, measuring several hundred meters across, large enough to pose a genuine regional threat. In 2029, Apophis is set to make a well-publicized and very close pass by Earth. But here is the critical distinction. Apophis is not a surprise. We have known about its existence for years, which has allowed for extensive tracking and repeated refinement of its orbit. The current calculations confirm that it will pass by safely, posing no risk of impact. The key lesson from Apophis is that because we have known about it for so long, we would have had years of runway to act if the math had pointed to a collision. This is what an effective warning system looks like when it has the benefit of a long lead time. The reason for this long warning is simple. Apophis is large. It is big enough to have been detected early and to be part of the near-Earth object catalogue that is now reasonably complete. This stands in stark contrast to 2026 JH2, which is small enough to inhabit the vast, mostly empty portion of the catalogue, and thus its warning was measured in days. Apophis and 2026 JH2 represent the two extremes of our current system. For the large object, we had decades of notice. For the small one, a long weekend. This raises a deeply unsettling question about the objects that fall in between, like those in the regional devastation class, around 140 meters in size. With only about 40% of these objects catalogued, whether we get years of warning or mere days for any one of them is, for now, largely a matter of luck. Yet, the case of Apophis offers more than just a cautionary tale. It also provides a glimmer of hope. It demonstrates that the warning problem is, in principle, entirely solvable. When an object is sufficiently bright and well-positioned to be detected early and tracked over a long period, our system delivers exactly what is needed: years of lead time, a confident orbital path, and the opportunity to act if necessary. This suggests the goal is not impossible. We are not struggling against an immutable law of physics that dictates all warnings must be short. Instead, we are contending with the present limits of our own technology. Our detection capability simply fades below a certain threshold of brightness. Below that line, the warning time collapses dramatically from years to days. Apophis lies on the bright side of this boundary, while 2026 JH2 falls on the dim side. Crucially, this dividing line is not a fixed feature of the natural world. It is a product of our current telescopic power and survey strategies, which means it is a line that we, with concerted effort, have the power to move. Our view of the cosmos is not absolute. It is defined by the instruments we have chosen to build, and just as critically, by those we have chosen not to. With better telescopes, we could push back the darkness, especially with instruments placed to see into the challenging glare of the Sunday. If we did, objects that currently appear with only a few days of notice might instead grant us years, or even decades, of warning. This calm, confident approach, known as the Apophis treatment, is not a special privilege reserved only for the largest asteroids. It is a level of security that could be extended to smaller bodies if we simply decided to lower the threshold of detection. We have a working example of our planetary defense system performing its job well, but we only receive this assurance for objects large enough to clear our current self-imposed bar. This reveals a crucial truth. Our present limitations are a choice, not an unchangeable destiny. The honest interpretation of a headline like "Newly discovered asteroid will safely pass Earth" is therefore more complex than it appears. A truthful translation, leaving nothing out, is this: we were fortunate in its trajectory. We did not render this object safe. Its existing orbit was already a miss, and we found it with just enough time to confirm that fact and observe its passage. Had the orbit been different, the few days of warning we received would have been the same. But they would have been days to watch, not days to act. We have proven once that we can alter an asteroid's path, but we have not yet constructed the tools needed to nudge a rock that is actually on a collision course with such short notice. This is the gap in our capabilities. It is not a conspiracy, nor an oversight by any single person. It is simply a machine that has not yet been built, leaving a void where one of humanity's most important creations ought to be. The flyby this Monday, along with the 7 or so other objects accompanying it this week, is simply the solar system behaving as it always has. It sends rocks through space, allows orbits to converge, and continues the very same process of accretion that formed the ground beneath our feet. The solar system's role in this cosmic dance is not going to change. Our part, the seeing and the doing, is the only portion of this equation that was ever up to us. And at this moment, our vision has a blind spot, and our ability to act does not yet exist. This brings us to a question that does not fade. On a Monday afternoon, an object the size of a building is set to journey between our world and the moon. It will pass closer to Earth than many of the satellites we have placed in orbit, and yet almost no one will notice. By Tuesday, it will have vanished back into the dark, and the headlines will have moved on. On the narrow question, the only one the headlines actually asked, the asteroid 2026 JH2 is indeed safe. This is true. You can let that particular worry go. Monday is fine. But the purpose here is to leave you with a question that does not disappear when the rock does, because that is the real subject. It has always been the real subject. The question is not whether 2026 JH2 will hit Earth. It will not. The question is the one we began with, now reinforced with everything we have explored. If the detection system that found this object is working exactly as it was designed, and working as designed still means a 70-foot asteroid can reach 1/4 of the moon's distance with only days of warning, then what honestly happens on the day the next one is not a near miss. We have walked through every piece of this. We know our catalogue of near-Earth objects is excellent for the giants, shaky for the city killers, and nearly empty for the size class that just flew past us. We know there is a blind spot in the direction of the sun, a region our ground-based telescopes physically cannot see into. And we know the Chelyabinsk meteor came through that exact blind spot with zero warning in our lifetimes over a populated city. We know that this week's wave of 8 asteroids is not the total number of rocks that exist, but only the 8 that were bright enough and well placed enough for us to catch. They are the visible portion of a population whose other half we cannot see. We know the convergence of these orbits on Earth's path is not an omen, but something far more permanent. The same accretion process that built the planets and has been resurfacing Earth with impacts for 4.5 billion years. It is a process that did not stop. Earth is still inside it. And we know that on the other side of the warning, on the question of what we do once we have seen, there is one proven tool that needs years of lead time, set against a warning system that frequently gives only days. There is no operational capability standing in the gap between them. We have a single successful science experiment, but no planetary fire department. And here is the thought I keep returning to, what I believe is the actual weight of this story. Detection, the seeing, is the part that works. It is incomplete, it has the blind spot, but it is real, it is improving, and every new survey telescope makes it better. The seeing is the success story of planetary defense. And yet, even this success story, on its best day, performing exactly as designed, handed us a 70-foot rock with a long weekend of notice. That is the good half. That is the half that is going well. The other half, the doing, the turning of a warning into an action, that half is not incomplete. It is absent. It is a proven principle and an empty space where the machine should be. So, the most truthful sentence anyone can say about an asteroid passing close on a Monday afternoon is not the one in the headline. It is not. It is safe. The most truthful sentence is, it is safe times this time. And if it had not been, we could not have done anything. We have known this, and we have not yet built the thing that would change it. The rocks keep coming. The orbits keep converging, because convergence is the rule this solar system has always run on, not the exception. We just watched 8 of them go by in a week, and we will watch more. And almost all of them, the overwhelming, reassuring majority, will slide past in the dark and harm no one, exactly as 2026 JH2 will on Monday. But almost all is not all, and the only variable we were ever given a hand on, the only part of this we were ever asked to decide, is whether the gap between what we can see and what we can do gets closed before the trajectory that comes back around is the one that does not miss. That is the question. It does not go away when Monday's rock does. It is still there on Tuesday, and it will be there every week there is a new wave of discoveries. It will keep being there, quietly, whether or not anyone is looking at it, until we either close that gap or run out of time to. And the strangest part, the part I will leave you to sit with, is that we are the first generation in the entire history of this planet that could see the question clearly enough to answer it. And so we see a generation that has, thus far, chosen